Materials known to mankind are huge in numbers. For the sake of easiness in understanding their nature, materials they are divided, they are grouped into different categories. This grouping, this division, this classification is always based on one or other property of the materials. Electrical conductivity is a property, an electrical property of the materials. It indicates the capacity of a material to flow electricity, current carriers or charge carriers. Based on electrical conductivity, the materials mankind knew are divided into three categories, grouped into three types: conductors, semiconductors, and insulators. Conductors are materials which have huge capacity to flow electric current carriers or charge carriers, whereas insulators are materials which have no capacity to flow electric current. Semiconductors are materials which are in between conductors and insulators. Their electrical conductivity is in between that of conductors and insulators. Aluminium, gold, silver, copper, these are all examples for conductors, whereas wood, mica, etc., these are all examples for insulators. When it comes to semiconductors, silicon, germanium, these are widely used materials in electronics, and these are examples for semiconductor materials. Their conductivity is neither large nor small. It is medium. When it comes to energy band diagrams of these materials, in conductors one can see the conduction band and valency band. These bands are not at all separated. In fact, there exists an overlapping between these two bands. It implies electrons which are in the valency band, they can be in conduction band too simultaneously. They can be free too. When electrons are free, they contribute to the conductivity. When it comes to insulators, there exists a gap, huge amount of gap between conduction band and valency band. It means, it implies good amount of energy is required to make a valency band electron free, a conduction band electron. Therefore, very few free electrons are available in insulators. For this reason, conductivity is almost nil. When it comes to semiconductors, in these materials also, there exists a gap between conduction band and valency band, but this gap is not huge. This gap is not large. It is small. Electrons, when given small amount of energy, they can jump from valency band to conduction band, making themselves available for conducting electricity, for increasing conductivity. When it comes to structure, internal structure of the semiconductors, we consider silicon and germanium as they are widely used to understand the internal structure of the semiconductors. Silicon and germanium are tetravalent. It means there exists 4 electrons in their outer orbits. Usually, all these 4 electrons, they are locked in covalent bonds, 4 covalent bonds, and they are not free. Some of them, however, they come out of the bonds by taking necessary energy from the heat that is available in the surroundings, leaving behind a vacancy in the covalent bond. This vacancy is called hole. Therefore, in semiconductors, most of the electrons, they are locked in covalent bonds. They are not free, but there exists some electrons which are free, along with some vacant slots in the covalent bonds, which are called holes. Both electrons as well as holes contribute to the conductivity. Electronic devices, semiconductors, the second part, series on semiconductor devices and circuits, lecture number 1.12. Diodes and transistors. These are 2 prominent electronic devices. Semiconductors like silicon, germanium, gallium arsenide, and several other such type of materials are being used to fabricate these devices. In the present session, the focus is on the structure, the electronic structure and crystal structure of these semiconductor materials, which go into the making of these devices, diodes and transistors. Now let us move further to the course session. We begin the session with properties of widely used semiconductor materials for the fabrication of electronic devices. We begin with elemental materials like silicon, germanium. These two belong to column 4 in the periodic table. Next, we move to binary composite semiconductor materials. These materials, they are formed out of column 3 and column 5, and some are formed out of column 2 and column 6 materials in the periodic table. Example for such type of binary composite materials, a list is given here: gallium arsenide, aluminum arsenide, gallium phosphide, zinc sulfide, zinc telluride, cadmium selenide. Another type of materials, ternary semiconductor composite materials. They are also used in the fabrication of electronic devices, semiconductor electronic devices. These ternary materials, they are formed out of elements that are there in column 3 and column 5 of the periodic table. Examples for such type of semiconductors are gallium arsenic phosphide, gallium aluminum arsenic. Quaternary materials are also there. Example also for such materials. One example is provided here: indium gallium arsenic phosphide. Notice this is a composite material. It is made out of indium, gallium, arsenic, phosphide. 4. That's why quaternary. Some more points, important points regarding silicon and germanium. Notice, before going further, widely used semiconductor material is silicon. Sometimes it is germanium. Other semiconductors that are mentioned in this table, binary, ternary or quaternary, they are used only in diodes which require to function under some specialized situations. Now, few points regarding silicon and germanium. Both are indirect band gap materials, hence not suitable for high frequency applications. Gallium arsenide is direct band gap material and widely used for high frequency applications like in the fabrication of LEDs, photodiodes, etc. What is indirect band gap material and what is direct band gap material? Consider energy band diagram of semiconductor. At the top is conduction band, at the bottom is valency band. When the conduction band electron falls into valency band, the electron disappears, a hole also disappears. This process is called recombination. During recombination, in addition to disappearance of electron hole pair, there takes place another phenomena too. That phenomena is emission of energy with certain frequency. Energy emitted, it is related to frequency of the energy through Planck's law, E equal to hf. This energy is equal to, or it is at least equal to gap energy, band gap energy. Now, what is indirect band gap material? In indirect band gap materials, electron doesn't fall directly from conduction band to valency band. It falls into valency band in steps. First, it falls from conduction band to some intermediate level that is existing in the band gap, and then from that intermediate level to valence band. In this case, emission of energy it takes place in two installments. The first installment is when it falls from conduction band to intermediate stage. But one can notice the difference of energy levels of the electron in the beginning and in the end. It is a very small, therefore frequency of emission is small. In the second fall also, this fall is from intermediate level to valence band. Here also energy difference is very small, therefore frequency in this case also it is small. If the fall is through an intermediate level in the band gap, then it is called indirect band gap material. In silicon, in germanium, this kind of thing happens. An electron in the conduction band, it falls into valency band in steps. And resultant, we have seen emission of energy in installments or in steps, and frequency of the energy is small. This can be noticed. In direct band gap materials, what happens is the fall of the electron from CB to VB is direct. So energy released, of course, which is equal to band gap energy. It is large. Naturally, frequency also is large. We conclude the discussion by mentioning that in direct band gap materials, recombination leads to higher energy, higher frequency radiation. In indirect band gap materials, recombination emits lower energy, lower frequency emission, radiation. Some more properties regarding silicon and germanium. As already mentioned, widely used semiconductors are silicon and germanium. Silicon, it is having 14 electrons. Germanium, it is having 32 electrons rotating around their nuclei. Electronic structure, therefore, for silicon, it is I1s2, 2s2, 2p6, 3s2, 3p2. In case of germanium, the structure is 1s2, 2s2, 2p6, 3s2, 3p6, 3d, 10, 4s2, 4p2. Notice the electrons in the outer orbitals, orbits, they are same. 3s2, 3p2. Here also 4s2, 4p2. 2, 2. 2 in S, 2 in P in both the semiconductors. So 4 electrons exist in the outer orbits. That's why they are called tetravalent. Tetra means 4. All the 4 valence electrons remain in covalent bonds. The crystalline structure of these semiconductors, it belongs to a category called diamond lattice. Each atom has 4 nearest neighbors. There exists 8 atoms per cell. First 2 points, they describe electronic structure. Remaining 3 points describe crystalline nature of silicon and germanium. Now gallium arsenide. It is 31 plus 33. Gallium is trivalent, arsenic is pentavalent. Trivalent means 3 electrons in the outer orbit, pentavalent means 5 electrons in the outer orbit. Tetravalent silicon is used as N type of impurity. Divalent beryllium and magnesium, these are used as P type of impurity. Gallium atoms, not arsenic ones, are displaced by impurities. The structure is zinc blende or sphalerite structure. FCC array with 4 asymmetric units in a unit cell. FCC stands for face-centered cubic. Now, here some information regarding lattices is being given. Simple cubic lattice, body-centered cubic lattice, face-centered cubic lattice. Simple cubic means 8 atoms at the corners of a cube. Body-centered means in addition to 8 atoms, 1 atom at the center of the cube. Therefore, total atoms now are 9. Face-centered. Each face of the cube now has one more atom at its center, in addition to 4 at the corners. A few points regarding crystal structure of silicon and germanium. The unit cell of diamond lattice is shown here. First FCC sublattice, second FCC sublattice. First FCC sublattice, it is indicated by continuous line. Second FCC sublattice, it is indicated by discontinuous line. Notice in the diamond lattice, one cell occupies a part of another cell, and there exists bonding between the atoms. That bonding is described in B, tetrahedral bonding structure. Here is an atom. This atom is bonded to 4 surrounding atoms through covalent bonds. All atoms, this atom, this atom, this atom, this atom, other atoms also, each and every atom in the crystal, it is bonded to 4 other atoms. A few points regarding diamond and zinc blend structures. It is obtained by starting with 2 FCC sublattices. One sublattice is displaced by 1/4 along the body diagonal of the other. Unit cell of this lattice consists of 8 atoms at the 8 corners and 6 atoms at the 6 faces, all belonging to the first FCC sublattice, plus 4 atoms of the second sublattice located within the first. Now, zinc blend. When the 2 sublattices are made of different elements, then it is called zinc blend lattice. Gallium arsenide is an example. When the 2 sublattices are made of same element, then it is diamond lattice. Silicon and germanium belongs to diamond lattice. Structure is the same, only difference is whether sublattices are made of same or different materials. In both, each atom is surrounded by 4 nearest neighbors. Diamond, zinc. First one is diamond. All atoms you can see, they belong to one type of material, silicon. In B is shown zinc blend structure. Certain atoms are shown with black spheres. Some are not black. Black are gallium atoms. Non-black are arsenic. So in the unit cell, you have 2 types of atoms. So it is zinc blend. Structure is the same. Structure of diamond lattice, zinc blend lattice, it is the same. Now a few points regarding notation that is followed in the analysis and also in the description of the functioning of electronic devices, semiconductor devices. So notation. N is used to denote free electron concentration. P is used to denote hole concentration. NP means electron concentration, free electron concentration in P type of material, P semiconductor. PN stands for hole concentration in N-type semiconductor. Electron concentration in P-type semiconductor, hole concentration in N-type semiconductor. These are called minority carrier concentrations. So NPPN, they denote minority carrier concentration. Majority carrier concentration. NNPP. NN means electron concentration in N-type semiconductor. PP means hole concentration in P-type semiconductor. Electrons in N-type semiconductor, they are majority carriers. Holes in P-type semiconductor are in majority. Hence, they are called majority carriers. Injected carrier concentration. NN prime, PP prime. NN prime means injected electron concentration in N-type semiconductor. PP prime means, or P prime P, means injected hole concentration in P-type semiconductor. To denote equilibrium values, O is used as subscript. Example, NP0, PN0, PP0, NN0. This can be considered as O or 0. Examples, NP0. NP0 means electron concentration on P side under equilibrium condition. Similarly, meaning can be given to other quantities also. Two types of semiconductors we encounter in the study of semiconductor electronic devices. One type is called intrinsic, another type is called extrinsic. Intrinsic means it is a pure semiconductor with no foreign atoms. Intrinsic silicon means in that material only silicon atoms exist, then it is intrinsic. Extrinsic means impure with foreign atoms. So silicon is there. Let us say to begin with it is intrinsic, pure. If you add some impurities, naturally, now purity of the silicon is lost. Inside silicon crystal slab, one can find, in addition to silicon atoms, foreign element atoms too. Then it is called extrinsic. In intrinsic semiconductors, in pure semiconductors, number of free electrons is equal to number of holes, always. And this number is equal to a constant. This constant is called intrinsic carrier concentration, Ni. Symbol is Ni. Ni is dependent upon temperature and also on material band gap. An expression is there for Ni. Ni square is equal to A naught T power 3 e power minus EGO by KT. T stands for temperature. Here also T stands for temperature. Notice in this expression, temperature is appearing at two places. Not only two, it exists inside EG naught also. So this is a temperature dependent constant. A naught is some proportionality constant. Ni is very small usually and 0 at absolute 0 temperature. Notice A naught is a material dependent constant. We come to the end of this session. Let us recollect the important points that are discussed in this session. Mostly the attention in this session is on electronic structure and crystal structure of the semiconductor materials, widely used semiconductor materials like silicon, germanium and gallium arsenide. Hope this session is useful to you. We meet again with a new topic in another session soon.